So in this video, we will be looking at Diophantine equations, and we're going to look at using factorization. So firstly, an introduction to Diophantine equations is that Diophantine equations deals with integers. So you get a normal equation with a few expressions, a few unknown variables like that, with x and y and stuff, but it will be different to algebra. Solving algebraic equations, because in Diophantine equations you deal with integers, and that really restricts a lot of things. So for example, like the simplest thing I can show you is that if a times b is equal to 3, and we say that a and b have to be integers, then you'll think like, oh, there are infinitely many possible values, because whenever you solve algebraic equations and a is equal to 3 over b, and then you'll think that there will be infinitely many cases, but no, because if you try to express 3 as a product of two integers, there's only 1 times 3, there's only 3 times 1, there's only -1 times -3, and -3 times -1, counting permutation, given that a and b, so there are only 4 cases, so our answers would be, following this, ab can only be equal to 1, 3, or 3, 1, comma, or so on, just following this. So it's like, actually I just write it out, because when you guys look back at this again, you're going to think there are going to be infinitely many cases, which is not correct. I'll just write it out. Yeah, so these are the only possible solutions. And for those who only only did number theory, this will be kind of, it's pretty obvious, but when you think that in such a vague equation, where you have one equation with two variables, you get quite a few number of solutions. And this is the basics of number theory, how it restricts so many things, and it makes things so much easier. Yeah, so that's why algebra and number theory are two completely different branches of math. So yeah, so here a times b were integers, but what if we have x times y plus 1 is equal to 2, and x and y are integers? Well, it's the same thing, because if y is an integer, then y plus 1 is an integer, so these two things are integers. And so it's an integer times an integer is equal to 2, and 2 can only be equal to 1 times 2, 2 times 1, -1 times -2, or -2 times -1. So yeah, so x can be equal to 1, y plus 1 is equal to, so x is equal to 1, y plus 1 is equal to 2, or x is equal to 2 and y plus 1 is equal to 1, and so on, like just following this. And it's like pretty interesting, because we thought that we need to have like integer times integer equals this, but we only need an integer expression times an integer expression equals an integer to do these to do this kind of casework. And you'll see later on, I'll just say it later, yeah. So our main motive, I've read it in a different color, our main motive is to factorize some expression, not the whole expression by putting everything on one side and making a 0, but we want an integer on this side. We want an integer on this side, and we want two expressions that are integers. So it doesn't have to be one variable that is an integer, but a whole expression that is always an integer. Like for example, y plus 1 is always an integer if y is an integer, and y squared plus 2 would also be an integer if y is an integer. So an integer expression given the initial conditions that were all given at the start of the problem. And then we can do this casework, because this integer can be expressed as can be expressed in only a finite number of ways of a product of two integers. So we can just plug them in. And then solve them simultaneously, or just solve them separately, and so on. So like, this is the main motive behind solving Diophantine equations using factorization, which I find pretty interesting. When I first learned this, this was one of my favorite topics because it was quite interesting. So yeah, having this in mind, so we're gonna be looking at in this series we're gonna look at techniques, simple techniques in factorizing an expression into two integer expressions, so that and then this equals to an integer. So we're going to try to do this so that we can do this casework. And you realize that when whatever problem we do, we will, using factorization, it will always end up in the same place. We're just doing the casework by plugging them in and so on. So yeah, I don't have any space, so I hope you guys have this down. But since this is a video, you can just go back and look at it again if you forget it. But we have to move on. So the first technique we're going to look at is factorizing equations. Okay, factorizing equations. I need to put this in a different color. Factorizing equations into the form x plus a times y plus b. And x and y have to be integers. So x and y are given to be integers. And also a and b have to be integers. Yeah. But remember, x and y are unknown variables and a and b are constants. So a and b are constants. So a and b are constants that are integers, and then x and y are unknown variables that are given, that are where the conditions are given that they have to be integers. So yeah, we're gonna try to factorize it into this form, and this is so if we get like this is equal to an integer, then we can just have x plus a is equal to some number, and then y plus b is equal to another number that both multiply to this. We can do that casework very easily. And actually, if we expand this, so we want to be able to factorize it into that form. We want to be able to factorize it into this form. So we're going to expand this to see what kind of expression it gives, actually. And we realize that it gives this. And at first glance, it looks pretty messy. But you'll see some symmetry because, you see some symmetry. Because if you look at this expression this time, we can, following this, b is equal to 1, a is equal to 1, and a times b is equal to 1, which is true. So we can factorize it into this form straight away. And for those with quick observation, you'll like kind of find this expression quite nice because it's pretty symmetrical. And it's pretty nice that you can factorize this into a really simple form. And not just in number theory, just remember this factorization technique because it's just very important. Yeah. So how does this help? So as I said before, being able to factorize will be good. So if x and y are given to be integers and a and b are given to be integers, these two are integers, and if they multiply to a certain integer, then we can do the restricted casework. So we're going to try and practice example instead of me just talking about this because it is important to know how to solve this actually. So let's say this. And x and y are integers, of course. And again, but this time we don't have the 1. So we look at this and we go like, oh, we can factorize it. It's like x times y plus a constant times x plus an integer times y. So we can factorize it into this kind of form. But we don't have the plus 1 here that we want. Because in this case, b will be 1 and a will be 1. So a times b is 1. So we need a 1 in here, but we don't have one. So we can't factorize it, but that's not how it works because we have a constant here, and all we have to do is just add 1 on both sides, and it makes no difference, and it makes it simpler actually because this will always be an integer, so it doesn't really change the identity, like not the identity, but like what kind of type of thing it is. So like it stays a constant integer, but then this becomes an expression that we can factorize. So actually adding the 1 is pretty beneficial. So we can factorize this into this form using this technique. So it's equal to 6. So x plus 1, so 6 is equal to 1 times 6, or 6 times 1, or 2 times 3, or 3 times 2. Actually, yeah, I'll just write it all down. But I'll just put the plus minus. Don't forget the plus minus. Like, if it doesn't restrict, then always don't forget the plus minus. Yeah, never forget the plus minus. So it's pretty simple. So x plus 1 is equal to 1, y plus 1 is equal to 6, or x plus 1 is equal to negative 1, and y plus 1 is equal to negative 6, and so on. Actually, there are quite a few cases here. So there might be a more elegant way to solve this problem, but this is one technique. And there's only a finite number of solutions, so it shouldn't take that long. And so if x plus 1 is equal to 1, then x is equal to 0, and if y plus 1 is equal to 6, then y is equal to 5. And we just repeat it. We just find x and y for each case. And we'll get a finite number of solutions, definitely. So this was, yeah, and you can go on and try it on your own. But yeah, for most of these kind of problems, when we arrive at the casework, I'll skip some cases because there will be cases when there are a lot of cases. So yeah, I'll skip some. But if you want to try it on your own, you can. But the basic idea, just like plugging it in and stuff, is really repeated. So I'll just skip some cases throughout this video and other videos. So yeah, that is how you do it. So what this tells us is that even if we get just a form of like x times y plus an integer times x plus an integer times y, then we can just freely add an integer to just make it factorizable. So for example, if we had like xy plus actually we're gonna get another problem later, so I don't have to do that. So actually, should we do another problem? Yes, we should do another problem, because now we have to look at, I'm gonna leave that there. I'm gonna leave that there, and then I'm just gonna erase these so that you guys can refer to it. So next problem is 1 over x plus 1 over y equals 1/3. And you can solve this problem in many ways. I can solve this problem in another way as well. But in this video, we're going to look at the technique we just looked at. So x and y are given to be positive integers. Positive integers this time. So not just integers where it can be negative integers, but positive integers. And this time we're going to have some restrictions, more restrictions in our casework, which is good because we don't have to do so much casework. So this kind of form of Diophantine equations, it looks different, but like let's try cross multiply and stuff. Like if we simplify it, then we get 3 times x plus y is equal to xy. And we realize that, I'll just expand this, but it really makes no difference because no, I'm gonna put everything on one side. So we realize that this form just leads to this form, which is yeah, so this form just leads to this form. So we realize that these kind of forms just lead to this kind of form, so we can just easily factorize it into this form. So we get it again. We get the x times y plus an integer times x plus an integer times y equals some integer. In this case, it's 0. So this means that since this side is a 0, even if we add an integer to it, it'll just stay an integer. So let's now add an integer that will make this equation, this expression, factorizable. So in this case, b is equal to -3, a is equal to -3, so a times b is equal to 9. So we're going to add 9 on both sides so that we can factorize it like this. And then if we factorize it using the above technique, we get this. Oh, I forgot to add 9 equals 9. So if we look at all the cases, we get 1, 9, we get 9, 1, we get 3, 3, we get -1, -9, -9, -1, and -3, -3. But So you can go ahead and look at all these cases, and then say they're all the solutions. But remember, x and y are not always given to be like any integer. Like sometimes the problem can go like, oh, it has to be positive integers. So that's why we have to be careful that whether the solutions give positive x and y. So here x minus 3 is equal to 1, y minus 3 is equal to 9, so I'll just write the solutions down in another color. xy is equal to 4, 12, and then if x minus 3 is equal to 9 and y minus 3 is equal to 1, then it's this. And if x minus 3 is equal to 3 and y minus 3 is equal to 3, then they'll be equal to 6 and 6. And then we can look at the other cases, but if we look at this, if y minus 3 is equal to negative 9, then y is gonna be equal to negative 6, which will violate this case. And then similarly, x minus 3 cannot be equal to negative 9. And if x minus 3 is equal to negative 3, then x is equal to 0, which again violates this case. So these ones don't work. They don't work. So these are the only possible solutions. These are the only possible, okay, I'll just not make a square. These are the only possible solutions. So if it says x and y are have to be negative integers or positive integers, then life becomes a bit easier, because like this, normally almost half of the solutions will be eliminated. So if you're good at observing these kind of things really quickly, then you'll be able to eliminate these really quickly. So yeah, today we just looked at one technique, where if you have this kind of form, which is such a common form, you'll see so many times in Olympiad math as well as basic competition math. So remember this technique, not only in number theory, but just everything else. But the essential idea behind using factorization to solve Diophantine equations is that you want an integer expression times an integer expression equals an integer, so that you can narrow it down to cases, and then you can easily solve it using casework, though it may be tedious at times. So yeah, that is the end of this video. So I hope you enjoyed it, and hope to see you in my other videos.